All right, we had this example in the last video. That was the matrix 4, 3, 6, 5 inverse, and it happened to equal 5 halves, negative 3 halves, negative 3, and 2. And the question is, how did we find this? How did I know this? And in fact, in some ways, it's easier to think about in terms of transformations. If you just think about maybe, this guy and 4, 3, 6, 5, that as a transformation, we have, or just even a system of equations. We have something like this. And this equals y1, and the second equation equals y2, right? And basically all you do is solve for x1 and x2. So if we solve, you basically have this augmented matrix, these coefficients, and then y1 and y2 in the augmented column. And then I just claim if you row reduce this, you should try it yourself. I claim that you end up with, the nice 1, 0, 0, 1 pattern there, and that you actually get 5 halves y1 minus 3 halves y2 here, and minus 3y1 plus 2y2 there. And so that translates into x1 equals 5 halves y1 minus 3 halves y2, and x2 is minus 3y1 plus 2y2. And so there you go. And then that leads back to, I guess that leads this equation right here. This set of equations leads back to this, because those are exactly the coefficients, right? The 5 halves matches that. The negative 3 halves matches that. The negative 3 matches that. And the 2 matches there. Okay. So that's really all it is. That's if you want to find the inverse of a 2x2 transformation, if it has an inverse. By the way, that's something we should mention. If it has an inverse, we needed to end up with this. We need to end up for being consistent no matter what the values of y1 and y2 were, right? And that only works if we get the 2 pivots. But if we do that and we just solve for x1, x2 in terms of y1, y2, we get the inverse immediately. Okay, and so it actually means we can do this in general because we kind of already did the general 2x2 system, right? So what is the inverse of the matrix A, B, C, D? Well, if we take the augmented matrix, we augment with the column y1, y2. We actually did this in an earlier video. I think we actually called these R. I think we called that R and we called that S in the video we did before. But we did it, and we ended up with, from video before, you were supposed to follow along, do it by hand yourself. We actually ended up with this. We ended up with the identity matrix, and then I think what we got was something like dy1 minus by2. Again, y1 and y2 were R and S in that video, over AD minus BC, and AY1 minus CY2 over AD minus BC. And that means x1, and I'm going to write this a little bit. I'm actually going to kind of separate out the y1 and the y2 in these. So x1 is d over AD minus BC times y1 plus negative b over AD minus BC times y2. And x2, if I rewrite this expression similarly, it's a over AD minus, wait, I think I have my y2s and y3, y1s backwards because I know this. In fact, I'm sorry, I miscopied this for myself. Let me fix this. This is bad. This is bad. This should have been, yeah, sorry about that. This should have been minus cy1 plus ay2 over AD minus BC. I think that matches the RS formula from the earlier video. So, okay, sorry about that. That means this is, so we have minus C. It's good that I know what the answer should be so that I can see when I messed up. And this is A over AD minus BC times Y2. And so in fact, these numbers here become the inverse matrix, the numbers in the inverse matrix. But notice that you have 1 over AD minus BC everywhere. So we can actually factor that out. So in fact, if we want to write this inverse, we can factor out this 1 over AD minus BC. And then we just have these numbers D minus B minus CA. And that's, so they go there, D minus B minus CA. And in fact, that is the general 2x2 inverse. Okay, so that's kind of a formula. That's kind of a nice formula. It's worth checking that if you multiply these two matrices, the original ABCD matrix, and you multiply it by this matrix, you actually get the identity. So in fact, let's see. So this, if I want to put it this way, I want to say that this matrix right here, this matrix is A, and then so this is A inverse. If this matrix is A without the minus 1, that's A inverse. So you should check. It's very satisfying to check that A times A inverse is actually the identity. And so is A inverse times A. So I would check that if I were you. But it's also worth noticing that, and we've actually come across this before earlier in the semester, that we need AD minus BC to be non-zero, right? So this also, we also get this condition. This is going to come up later. This matrix is invertible if and only if AD minus BC is not 0, because otherwise we can't divide by 0, right? And we actually saw this, that this meant, this actually is equivalent to there being 2 pivots in the matrix when we row reduce this matrix. Because if we saw that if AD minus BC was 0, then somehow the second column was a multiple of the first column. Right, you can sort of rearrange. You can rearrange this into something like A over C is not equal to B over D. And so that's exactly saying that this column, these two columns are not multiples of each other. But I will say that this has a very special name, which you've probably seen before, but this is called the determinant. And we're going to see it later again. The determinant of A. So for a 2D, for a 2D matrix, the determinant of the matrix ABCD is defined to be this expression AD minus BC, which is this thing with the cross. You do A times D, and then you do minus B times C, like that. And this is by definition. This is sort of defined to be this AD minus BC. And it's useful. It determines lots of things. That's why it's called the determinant. And so, right. Okay. So so this is kind of the upshot here, is that we have this general inverse formula that's sort of nice. I'll just go ahead and say this, that the way people think about this is that you swap these two, right? Because you swap A and D swap with each other, and then B and C become negative themselves. And then you have the 1 over AD minus BC. And you can check that, in fact, this formula works all the way up here. The AD minus BC here is 20 minus 18, which is 2. That's where those halves come from. If you swap these two, you get 5 and you get 4, but it's really 4 over 2 because you're dividing by the determinant. And if you make these two negative, you get minus 3 and you get minus 6, but you're dividing by 2. And so this becomes minus 6 over 2, it's minus 3. Anyways, so this actually, one reason I was able to come up with this so quickly is because I know this formula, and so I could just write down the inverse matrix inverse transformation almost immediately. But it's nice, it's a curiosity. It's not something necessarily that deep, but it's nice that you can sort of have this nice formula. And once we get to like 3 by 3 matrices, the inverse formula will be much, much less nice. There are somewhat nice formulas, but it's definitely less nice. So, okay, I'll stop that video there.